The ballistic reality of Artemis II. Artemis II will not actually orbit the moon. While the public narrative focuses on the crewed return to deep space, the mission is fundamentally a high-energy ballistic loop designed to ensure the crew returns to Earth even if every engine on the Orion spacecraft fails. This is the free return trajectory, and it is a rigid engineering constraint, not a stylistic choice. The safety logic of the U-turn. To understand the mechanics, you have to look at the Orion service module propellant budget. Entering a stable lunar orbit requires a massive retrograde burn to shed velocity, followed by another prograde burn to leave. By staying on a free return path, the mission uses the moon's gravity as a natural U-turn. The spacecraft passes behind the lunar far side and is whipped back toward Earth by the moon mass. This preserves the entire primary engine fuel load as a reserve, a critical safety margin for a first-in-class crewed flight. But this safety comes with a specific orbital resonance requirement that the ICPS upper stage must hit perfectly. Why the Earthset is rare. There is a common misconception that the Earthset happens because the crew is circling the moon. In reality, the Earth vanishes behind the lunar limb because Orion's altitude at Perihynthon, the closest approach, is roughly 7,500 kilometers. At this height, the moon's curvature relative to Orion's velocity vector creates a very specific occultation timing. If the mission had entered a low lunar orbit like Apollo 11, the Earth would rise and set every 2 hours. On Artemis II, it happens exactly once. This single event is the ultimate thermal stress test for the spacecraft high-gain antenna, as it loses line of sight with the Deep Space Network. The hidden Delta-V constraint. The skepticism comes when you look at the total Delta-V capability of the SLS Block 1. It is pushing the Orion ICPS stack to a TLI velocity of about 10.4 kilometers per second. If NASA had opted for a standard polar orbit, they would have sacrificed the passive return capability entirely. In an engine-out scenario during an orbital insertion burn, the crew would be stranded in a permanent lunar orbit with no hardware-native way home. The free return trajectory is a 10-day hardware validation loop that prioritizes heat shield performance and life support reliability over orbital science. This choice highlights a conservative shift in mission architecture compared to the Apollo-era risk profile, where engine reliability was assumed rather than hedged against. The safe-fail engineering shift. The Artemis II trajectory reveals that NASA is no longer building missions around maximum exploration capability, but around maximum survivability for hardware maturation. By prioritizing the free return trajectory over a lunar orbit, they have traded secondary science objectives for a 100% passive abort mode. This trajectory, and the Earthset it produces, is the physical manifestation of the Orion service module's current performance limits and the SLS launch window constraints. It proves that in 2026, we are still in the testing phase of the deep space transportation system, where gravity is used as a safety net because our propulsion margins are still tight. The real metric for Artemis III success won't be the landing itself, but whether the service module's upgraded propellant tanks finally allow us to break free from this passive return dependency. We will see the first signs of this shift during the next Gateway refueling simulation scheduled for late 2026. Subscribe for more.